Okay, so hello to everyone. I hope you enjoyed your break. My name is Federico, and I'm going to talk about global variables in C++. So, the first slide about global variables is about constants, and the fact they are often praised in our code because they help to avoid having magic values in our code. I mentioned constants because often there are global variables too. Contrary to constants, global variables are often labeled as bad. The reason is when talking about globals, we normally are talking about mutable globals variables. And if you're not convinced that they're bad, at least let's say that they have some known disadvantages. In particular, in bigger application, when working with mutable global variables, it gets harder to see how the program works because it's more difficult to track where the state changes. It also makes, for example, testing more difficult. But those points do not hold for global constants. Nevertheless, C++ is a very complex language, and constant globals can be problematic too. The most known problem is the static initialization order fiasco, the fact that the order in which variables are initialized is not defined. But today I'm going to talk about another problem that affects constants too. So let's look at a very simple example. In this case, I've defined a constant std string, which is initialized with a literal value. As it is initialized with a literal string, this variable is not affected by the initialization of the fiasco. Other variables that depend on answer of life might be, but answer of life itself doesn't have this issue. And even if this code is pretty trivial, it can be problematic, as it might involve undefined behavior. Common observations are double freeze when the program exits, generally memory leaks, or the fact that the program is using twice as much as memory as expected during the runtime. When do those issues occur? They occur if you have a project structure like the one in this image. You have a global variable defined in a static library. This library is linked in 2 or more shared libraries, and those are used in your main application. I want to show some examples how global variables behave when they're used in such a context. I'm unsure if it would be better now to answer the questions immediately or after. Oh, yes, you should be seeing something. Okay. I'll continue. Yeah. So the first example is, again, very trivial. The definition and the declaration of the global instance are both in the header file. I've put the example on Godbolt, the compiler explorer. Oops. As it makes it easy to play with different compilers, runtimes, project structures, and so on. There's a central CMake list file, which defines the project structure as shown in the previous image. We have a static library named lib0, 2 shared libraries, lib1 and lib2, that both depend on the static library, and at the end the main executable that uses both shared libraries. Most code is irrelevant, just some function calling other function that at the end of the day call the access the global instance. The relevant part is the header file of the static library. Here's the structure with a user-defined constructor and destructor and the global instance. What's relevant in the constructor and destructor is that I'm printing the address of the object followed by a string literal, And that's pretty much it. In this, here it is possible to see the output of the compiler and the output of the program executed, printed at runtime. And as we can see, there are 4 calls to the destructor on 4 different addresses. Thus, so far so good, because we have 4 different objects, they do not interact with each other, everything is good. Except for the fact that normally when defining a global instance, we would like to have only one of it, and not multiple, for example, to reduce the usage of resources. Thus, it's not the main example of global variables one would expect. So another one would be declaring a static member variable. In this case, we will effectively get only one instance, but destructors and constructors are still executed more than once. As you can see, the structure is the same. I've put the global instance as a static member variable inside another structure. The definition is here, and in the corresponding CPP file, it's possible to see the declaration. And in this pane, you will see that the destructors are executed only twice and not 4 times as in the other example, but the address of the object is the same. Thus, we have only one global instance, but the destructor is executed more than once, which is undefined behavior. Now, one might say, why am I using a static member variable? Contrary to Java, we have other tools for defining global instances. Why not use, for example, extern? Unfortunately, using extern doesn't change anything. Also in this case, we will have only one instance. Constructors and destructors execute more than once on the same object. Again, we can see here the destructor executed on the same object. Before finding out what's the root cause of this behavior, I want to stress why I find those examples extremely problematic. It's the fact that there's no particular code smell. Defining a global variable shouldn't be a strange thing, especially if it is a constant. And we're invoking undefined behavior, and the fact that we're invoking it seems to depend on external factor which we cannot control. There's no indication that it's problematic to create a global instance of the class I designed. I'm simply printing the address and the string from the constructor and destructor. There's no indication that it's problematic to compile the code as a static library, nor that it is problematic to link it to a shared library. And also note that it didn't load any libraries by hand. Everything has been done automatically by the compiler at runtime. But even if it's possible to disallow creating a global instance of this particular class, it would, in my opinion, mind a design decision of a C++ language compared to others. Normally, when designing a class, the same type can be used for creating function parameters, global, local, member variables, heap allocated variables, and so on. And except that now in this case, normally everything just works as expected. If you think about the std string class, there's no reason to expect that it should behave differently when used on the stack or on the heap as member variable, parameter, and so on. And it's a good thing. So let's look now at what's the issue, the underlying issue that leads to the undefined behavior. It's 2 things. The first is symbol visibility, and the other is the runtime initialization and deinitialization. Normally, when libraries are loaded from the file system, if the same symbol is found more than once, those symbols are merged together. This is normally not a problem. For example, it's much more common for functions to appear more than once, and still we do not have any type of undefined behavior. The difference compared to function is that global classes have some code that is executed automatically and change some state. as visibility seems to be the root cause, the follow-up question would be how can we change it to avoid this type of behavior that obviously we do not want. And there are in fact many ways to change the visibility of a symbol. For example, through extern, static, inline, const, or compiler-specific keywords like the del export and the del import. Compiler flags like the -f visibility of GCC and Clang, using an anonymous namespace, or through our other means, indirectly. For example, if one uses const expr implies const, and const affect the symbol visibility. So there's more than one way, and they are not independent from each other. So it's not possible to use all of them together or one specific in all cases. Again, I would like to show some examples how it's possible to avoid the undefined behavior. The first is again the simplest one. It would be not to export anything. For me, not exporting anything means putting all the private data in an anonymous namespace. In this example, with the given project structure, instead of one global instance, we would then having two independent instances. As you can see, I've removed the global instance from the header file and put it in the corresponding CPP file in an anonymous namespace. And in this pane, we can see again the output, and we have in fact two instances with two different addresses. I mean, two instances, and on each instance, the destructor is executed only once. So far, so good. So you might wonder if the anonymous namespace is really necessary. In fact, in this case, it's not. I can remove it, and the output would be the same. We still have two instances. It is relevant if your variable is not constant, because const changes the linkage in C++. So by removing const, we will get only one instance where the destructor is still executed twice. So again, the case we do not want. It can be avoided by using the static keyword, as it changes again the linkage. Exactly. And of course, we can put it all together in this case, static and const. Static, it's simply redundant, and the anonymous namespace too. For simplicity, I think it's much easier to say just put everything that should be private in the anonymous namespace instead of using the static keyword, which depending on the context has a different meaning. Another way for avoiding the issue would be changing the default visibility. I mentioned that the GCC and Clang compiler support a -f visibility flag. In this case, if I take again the example with the external keyword and change the default visibility, thus no change in the source code, I'll get two global instances, destructor and constructor, and they are then executed only once per instance. Exactly, here's the header file. As you can see, there's the structure, the extern instance, and the corresponding line in the CPP file. I've made no code changes in C++ code. The only changes are structural in the CMake list, where I tell the compiler to set the default visibility to hidden. And in this case, we can see that we have two global instances as the addresses are different. Another way would be to use a singleton. Depending on the environment, we would get 1 or 2 instances. And by environment, I mean if the default visibility is set to hidden or not. In the first, the fact that the function is declared inline doesn't change anything. In the first example, the visibility is set to default, thus it did not change its value. And as we can see, there's only one instance, and the destructor is also executed only once. In the second example, the visibility is set to hidden. I did not change any C++ code, and there are two global instances. And if you really need to have only one global instance for the whole application, we can export the function that defines the singleton, and we would have only one instance with the destructor executed only once. Another possibility, since C++ 17, is to use inline with a variable. It behaves very similar to the singleton. That it means that depending on the environment, we will get 1 or 2 separate instances. In this case, we have default visibility, and we will have only one instance. And in the case we set private as default visibility with no changes in the C++ code, there will be 2 global instances. If we again, like in the singleton case, if we absolutely want to have only one symbol, only one instance, it's possible to export the symbol, and we will have again only one global instance. So it's time to draw a couple of conclusions. The first one is that there's more than one way for creating global instances. Depending on your type, there may be even more. It's a good idea to set the default visibility to hidden, as it helps a lot to avoid undefined behavior. If possible, avoid exporting global variables directly, constants included. Again, when talking about global variables, most of the time we mean mutable globals. In this case, constant globals too. Unless those constants are true constants. In that case, it's a great idea to use const_expr, not because it changes the linkage through const, but because it means that there's no code executed at runtime. Thus, those symbols behave like function symbols. They make me merge together at runtime, but nothing bad happens. So that was pretty much it. Are there any questions? Okay, apparently not. Either way, I'm here, so you can also talk to me later. Thanks.